Hello students, welcome to EPG Pashala. I am Dr. Sumalai Roy from University of Delhi from the Department of Physics and Astrophysics. Today we are going to talk on module TGA, which stands for Thermo-Gravimetric Analysis, under the paper Characterization of Nanomaterials 1 or COM1. So students, let us see what we are going to learn in this module. We will learn about the principle of thermogravimetric analysis, or in short TGA, different types of TGA. We will learn sample preparation for TGA. We will learn about the instrumentation with block diagrams. We will also learn the calibration of mass in this TGA, and we will learn introduction of the TGA curves and how to analyze them and the factors affecting the curves, and also application of this TGA. TGA stands for Thermo-Gravimetric Analysis. TGA is a technique which measures change in mass of the material as a function of increasing temperature, that is in scanning mode with constant heating rate, or as a function of time, which is in isothermal mode with constant temperature or constant mass loss. This change of mass is due to both physical and chemical phenomena like absorption, sublimation, vaporization, oxidation, reduction, and decomposition likewise. Types of TGA or thermogravimetric analysis. There are three types of TGAs. One is dynamic TGA, two is isothermal TGA, and the third one is quasi static TGA. The first one, dynamic TGA, in this case, sample is placed in a condition of continuous increase in temperature at a constant heating rate, that is, normally linear with time. Now, in case of the second one, isothermal TGA, sample is placed in a condition of constant temperature for a period of time during which change in weight is recorded. Number 3, which is quasi-static TGA. In this case of quasi-static TGA, sample is heated to a constant weight at each of series of increasing temperature. Principle: a microbalance is used to measure the mass change of a sample as a function of temperature or time under a defined and controlled environment with respect to heating rate, gas atmosphere, flow rate, crucible type, etc. Plot of weight change against temperature is called thermogravimetric curve or thermogram. Instrumentation. Medium TGA equipment has a sensitive balance, usually a microbalance for continuously measuring sample weight, a furnace surrounding a sample holder, and a purge gas system for providing inert or reactive temperature. A computer generally controls the furnace and the data. Data means sample temperature versus weight, and the data is collected and procured by computer. Balance is designed so that a change in sample weight generates an electrical signal proportional to the weight change. The electrical signal is transformed into weight or weight loss by the data processing system and plotted y-axis of the thermal graph. Instruments are available that allow the user to provide one atmosphere for the balance and another for the sample or the heater area and control the pressure as well. Most instruments also have ability to use isothermal or dynamic heating and cooling cycles, and some can also be programmed to hold a specific temperature once a change in mass is detected, then maintain the temperature until there is no further change and resume the heating program. TGA results like DSC can vary greatly depending on sample and experimental conditions, which can make it very difficult to compare the work of one researcher to another. Figure 1 shows a block diagram of TGA. Here you can see on the top there is an atmosphere control, and the furnace, you can see inside the furnace there is a sample holder and there is a temperature sensor attached to it. With the temperature sensor we have a recorder, and the recorder is connected with balance control, which is recording the balance, and the furnace is connected to a furnace temperature programmer. There are two possible configurations of balance and furnace, that is vertical furnace and is horizontal furnace, and both of these suffer from drift with the increase in temperature. Vertical configuration suffers from buoyancy effect due to change in gas density with temperature, and horizontal configuration was designed to minimize the buoyancy effect, but it experienced change in length of gauge rod connecting the sample to the balance as the temperature changes. Buoyancy effect is due to the force exerted by fluid that opposes the weight of an increased object. Modern instruments that heat at rates of 10,000 C per minute are available, and commercial instruments that heat rates of the order of 2000 C per minute from room temperatures to about 12,000 C. Cooling by forced air can be done at 500 C per minute, that is centigrade per minute. Now, sample preparation. Maximizing the surface area of the sample in a TGA pan improves resolution and reproducibility of wet loss by the temperature. The sample weight affects the accuracy of wet loss by measurements. Typically, 10 to 20 mg of sample is preferred in most applications, and if the sample is volatile, then 20 to 100 mg of the sample is required. The instrument have a baseline rate of plus minus 0.25% of a 10 mg sample. Calibration. Mass calibration is performed at room temperature by using standard masses. Removal of a standard weight on the sample holder, where the recorded change in mass is calibrated to the mass of the standard weight. The drift in baseline upon heating should be checked by a measurement using a blank sample pan. Following the measurement with a blank, a standard sample which decomposes quantitatively by several well-separated reaction steps is subjected to the same measurement, that is heating rate, sweep or carrier gas flow rate and type. Final temperature. The corrected mass change is constructed by subtracting the apparent mass change as a function of temperature from the sample under the study. The experimentally corrected mass loss should be confirmed and in good agreement with the calculated mass loss from the reaction stoichiometry. Kinetic theory. Transformation rate d alpha dt varies linearly with temperature dependent constant kT and the temperature independent function of conversion f alpha for heterogeneous solid state reaction. It can be defined as follows: d alpha dt is kT times f alpha. Temperature dependence of the rate constant is usually described by the Arrhenius equation. The mathematical description of the data is defined in terms of three kinetic parameters as pre-exponential factor capital A, the activation energy capital E, and an algebraic expression of the kinetic model in function of the conversion alpha and f alpha. So d alpha dt is a into e to the power capital E by capital RT into f alpha. At the same time, beta is dt by dt, d capital T by d small d, which is a constant, where beta is the heating rate. By inserting this term into equation 2, the above rate expression can be converted into non-isothermal rate expressions describing reaction rates as a function of temperature at a constant beta. Equation 2 can be transferred as follows. d alpha dt equals to 1 by beta into capital A into e to the power capital E by capital R into capital T into f alpha. The integration of equation 4 up to conversion alpha gives directly 0 to alpha integration d alpha by f alpha equals to the function g of alpha, which is equal to a by beta integration from t0 to t e to the power minus e by rt into dt. According to non-isothermal isoconversional methods applied by Ozawa, Wall and Flynn, which is described in the reference 16 and 17, using the Doyle's approximation of px, which is described in the reference 18. The activation energy can be determined by assessing the temperatures corresponding to fixed values experiments at different heating rates. Log beta equal to log of A into E by R into G alpha minus 5331 minus 1052 into E by RT. The activation energy capital E can be calculated by plotting log beta versus 1 by T. In order to obtain reaction order, Avrami theory, which is described in the reference from 19 to 21, studied and the non-isothermal data were variation of the degree of conversion with temperature and heating rate can be explained as alpha t equals to 1 minus e to the power kt upon beta into n. Taking double logarithm of both sides of equation 7 with substituting Arrhenius equation gives log of minus log of into of 1 minus alpha t equals to log a minus e to the e by rt minus n log beta. A plot of log of minus log of 1 minus alpha t versus log beta, which is obtained at the same temperature from a number of isotherms taken at a different heating rates, should give any straight lines. The slope will have the value of the reaction order or the Flynn-Wall-Ozawa exponent n, which is described in 16 and 23 references. Extra aspects of the technique apply to examine the process that is explained by Ozawa, which is given in reference number 24. This is an example of Tga curve, heat decomposition mass curve of wavelite, which is calcium oxalate monohydrate, is shown in figure 2. The successive plateaus signify the development of anhydrous salt, calcium carbonate and calcium oxide respectively, and can be given by following chemistries. The first equation A is CaC2O4 or H2O converts to CaC2O4 plus H2. Then B CaC2O4 converts to CaCO3 plus CO, and C CaCO3 converts to CaO plus CO2. The thermogravimetric curve signifies that removal of water starts at 100 degrees centigrade and removal of carbon monoxide at 4450 degrees centigrade and carbon dioxide at 600 degrees centigrade. Tg curves. The plot of weight by mass against temperature or time produced by a thermogravimeter is called thermogram. There are 7 types of Tg curve obtained from Tga as shown in figure 3. 1. There is no decomposition with loss of volatile products. 2. The rapid initial mass loss is characteristic of drying, that means dry the sample and redo the experiment. Number 3. Single stage decomposition. Number 4. Multi-stage decomposition with relatively stable intermediates. Number 5. Multi-stage decomposition with no stable intermediate product. However, heating rate effect must be considered. At low heating rate, type 5 resembles type 4. Type 6, gain in mass due to reaction of the atmosphere, for example oxidation of metals. And type 7 is oxidation product decomposes again at higher temperature. This is not often encountered. Formalized Tg curves. 1. Plateau. A plateau AB in the figure is a part of the Tg curve where the mass is essentially constant or there is no change in mass. Number 2. Procedural decomposition temperature. The initial temperature Ti, which is B in figure, is the temperature in Celsius or Kelvin at which the cumulative mass change reaches a magnitude that the thermovalence can detect. Number 3. Final temperature. The final temperature is that temperature in Celsius or Kelvin at which the cumulative mass change reaches a maximum. Information from Tg curve. 1. Plateau. A region of no mass change indicates the thermal stability of the sample or the substance. Thermal stability is the ability of a substance to maintain its properties as nearly unchanged as possible on heat. This information about thermal stability is significant for engineers as they know the temperature ranges of in which substances like alloy, building materials, polymers, etc. can be used. Second information is weight per mass loss. Heating a sample is into a given temperature causes to lose weight per unit mass. Mass per weight loss is informative to inorganic chemists who can then determine the composition of substance of the sample and understand the reaction involved in decomposition. And number 3 is procedural decomposition temperature. By looking at thermogram, one can determine the procedural decomposition temperature Ti, indicating the decomposition or evaporation of the sample or the substance. Fourth is composition. Weight per mass loss by heating helps determine the composition of substance of the sample. Also allows analytical chemists to identify unknown compound or determine the amount or the percentage or the weight of a compound in mixture of different compounds. Factors which affects the Tg curve. Number 1, the instrumental factors. It depends on the furnace atmosphere, flow rate, heating rate, geometry of the pan and furnace material of the pan. Nearly heating rate of 3.5 centigrade per minute is usually recommended for reliable and reproducible TGA. Sample characteristics. It depends on the mass. Small mass of sample is recommended. Particle size. You have to make fine powders. Sample history or pre-treatment. Packing. Make compact solids. Thermal conductivity. Heat of reaction and sample purity. There are several processes occur in TGA which leads to weight loss and gain as shown in figure table 1. Now there is a list. On the left hand side it is showing the process. On the right hand side there are 2 columns which shows that which one is a loss and which one is a gain. That means weight loss and weight gain. Now the process number 1 is adsorption or absorption. There is no loss of weight but there is a gain of weight. For solid gas reaction there is a loss of weight as well as a gain of weight. Then in magnetic transitions there is loss of weight as well as gain of weight. In desorption or drying there is only loss of weight. Dehydration and dissolution there is also only a loss of weights. In sublimation there is only loss of weights. And in vaporizations the same, there is only loss of weights. And in solid state reaction there is only loss of weights. Applications of TGA. So the first application is thermal stability. Related materials can be compared at elevated temperatures under the required atmosphere. Tga curve helps to explicate decomposition mechanism. B is materials characterization. Tga curves can be used to fingerprint materials for identification or quality control. Number C, compositional analysis. By a careful choice of temperature programming and gaseous environment, many complex materials or mixtures can be analyzed by decomposing or removing their components. For example, filler content in polymers, carbon black in oils, and carbon in coals, and the moisture content of many substances. D. Kinetic studies. A variety of methods can be used to analyze the kinetic features, weight loss, or gain through controlling the chemistry of predictive studies. And number E, corrosion studies. TGA provides a means of studying oxidation or some reactions with other reactive gases or vapor. So students, let's now summarize what we have learned in this module. In this module, we introduced TGA and learned about its principles. We learned what are the different types of TGA and explained their differences. We learned about the basic instrumentations and also we learned how to analyze a TGA curve or a thermograph.